Hi, my name is Rick Eads, and today we're going to talk about PCI Express technology version 5.0 with a preview to version 6.0.
For today's discussion on PCI Express, we'll start with PCI Express 5.0, giving you an overview of the development timeline and some electrical details. We'll talk about transmit test tools, and then we'll give you a quick preview of PCI Express 6.0. PCI Express technology has seen significant improvement since its introduction in 2002, averaging about 3 years between doubling the performance of the PCI Express specification. Most recently, the rate of improvement has increased dramatically. PCI Express 5.0 at 32 gigabits per second doubled the performance of PCI Express 4.0, and that specification was completed in about 2 years. Similarly, PCI Express 6.0 doubles the performance of PCI Express 5.0 by moving to PAM4 technology. And again, we expect that PCI Express 6.0 will have its specification completed within a 2-year time frame from the time that project was first announced. Looking at this slide, you can see that the increase in the performance of PCI Express and the decrease in the time that it has taken to double the performance of the technology is strongly driven by major trends within the industry, specifically in the use of artificial intelligence and co-processors, the emergence of the cloud and its contribution to mobile computing, also the growth in enterprise servers, and especially the transition of storage devices to use PCI Express technology have been important drivers demanding quick and rapid improvements in the performance of PCI Express technology. Along with improvements in overall PCI Express performance have been incredible advances in the signal integrity technology and measurement sciences associated with demonstrating conformance to each revision of the specification. Here you can see how we have observed what amounts to eye shrinkage, or the closure of PCI Express eyes, going from early PCI Express 1.0 out to PCI Express 5 and now PCI Express 6. You can see the dramatic reduction in the eye diagrams while we're still trying to maintain a post-equalization and post-forward error correction BER of about 1 error in 10 to the 12 bits. So the time is shrinking between each new successive generation, which is making it a challenge to the industry to be able to step up to the advances in measurement science and performance requirements demanded by the new technology. The PCI SIG consists of 9 member companies that form the board of directors. Keysight is the only test and measurement company that has ever served on the PCI SIG board of directors, and it is the responsibility of the PCI SIG board to direct the activities of the PCI SIG's efforts in developing new specifications. Here you can see that PCI Express 6.0 is the work product of several work groups that are organized by the board of directors. The main 2 groups that do this work are the electrical work group and the protocol work group. Combined, those 2 groups are responsible for creating the base specification for PCI Express 6.0. It is worth mentioning that when we say a specification has reached the 1.0 level, that we are typically associating that discussion with the base specification only. And that means that when PCI Express Gen 5 went to version 1.0 in May of 2019, what we had finished was writing the specification that described the performance of the silicon. But it wasn't until June this year that the card electromechanical specification, or the system specification, was released at version 1.0. So that took an additional 2 years. The card electromechanical specification defines operation of PCI Express at the connector. And yet we are still working on the PHY test specification, which defines the tests that are necessary to get a device on the PCI SIG's integrators list. The goals of PCI Express 5.0 really are about doubling the performance of PCI Express 4.0. In fact, one way to describe PCI Express 5.0 is that it is really PCI Express 4.0 with a speed improvement to 32 gigabits per second. Now, in reality, it's a little bit more than that because we had to add some additional features that would allow us to go to the higher speed. For example, the exit from electrical idle ordered set, or EIEOS, had to be changed to maintain the same frequency or timing that we use for the EIEOS signaling. But overall, the encoding remains the same at 128, 130-bit encoding. The loss budget did substantially increase, so we now have a target channel between 35 and 36 dB. And to achieve that, we had to do a couple of things. One is extensive equalization. Another was reducing the amount of allowable jitter by a factor of 2. It's reducing the reference clock phase jitter by a factor of 3. And overall, we had to improve the CTLE and DFE equalization substantially. We added another tap of DFE, for example, in order to help us achieve the target bit error ratio of 1 error in 10 to the 12 bits. Now, one reason I think that we were able to achieve this in a 2-year time frame from the announcement of Gen 5 until the completion of the spec was that we were able to leverage the work we had already done in describing new test methods for transmit testing and receive testing that were pioneered with PCI Express 4.0. So with PCI Express 5.0, we take what we learned with Gen 4 and we bring it forward to operate at 32 gigabits per second. In the next section, we'll talk a bit about PCI Express 5.0 Chem. This comes from the card electromechanical specification and represents some of the latest information about fixtures and test methods. The card electromechanical specification defines the operation of PCI Express technology at the connector. And here you can see photographs of the PCI Express 5.0 card electromechanical test fixtures. Now, let me tell you, these fixtures are a work in progress. And what you see here are the revision 2.0 test fixtures. The PCI SIG is going to release version 3.0 or revision 3.0 of these test fixtures in Q3 of 2021. So you should see an update. They still will look substantially similar to these because the changes are small but have to deal with both usability as well as signal integrity. One of the things that you'll notice that is very different from these test fixtures versus what we used for PCI Express 4.0 is the use of MMPX connectors from a company called Uber Sooner. These are special high bandwidth, high durability connectors that help to facilitate the higher bandwidth requirements of PCI Express 5.0. But we will use these fixtures in a similar fashion as to the way we use these fixtures with PCI Express 4.0 from both a receiver test and a transmit test perspective. First, let's talk about transmit test. And one of the things that we want to discuss is that when we are testing a PCI Express 5.0 system or add-in card, we need to test the transmitter looking at the entire length of the channel. Now, the test fixtures themselves comprehend some portion of the test channel, but it's not complete. So we need to make very precise measurements of all of the elements of the test fixturing. This includes the compliance load board or compliance base board, the loss associated with the MMPX connectors, any amount of cable loss, and the allowable package loss. We total all this up and we subtract it from 37 dB, which is the worst case channel. And then with whatever is left over, we have some test files of S4P transfer functions, which are provided by the PCI SIG that we add via an embedding function in the real-time scope, just as we did with Gen 4, for example, with package models. And we apply these S4P files, which add additional loss so that the end-to-end loss from the budget that's allowed for a system motherboard to the measurements being made on the real-time scope account for a total loss of about 37 dB. And this is how we make then the signal integrity measurements for the system motherboard. To help facilitate transmitter test measurements for PCI Express 5.0, Keysight offers the D9050 PCIe transmitter test application for real-time oscilloscopes. This allows you to test your PCI Express device both according to the base specification for silicon or against the card electromechanical specification for adding cards or motherboards up to speeds of 32 gigabits per second. You're allowed to do signal quality measurements. You can test presets. You can test with SSC on or SSC off. You can also test reference clocks according to the phase jitter requirements for the Gen 5 specification. One of the new capabilities that was added to the PCI Express 5.0 TX test application was the ability to embed the PCI SIG developed S parameter files as transfer functions using our Infinisim tool, which is part of this application. So I'd mentioned that each test fixture is slightly different. Each set of cables is slightly different. So you have to make measurements specific to your particular individual card electromechanical test fixture set and cable set. And then based on those measurements, you can select from one of a number of different S parameter files to make sure that your maximum loss is being applied to the test signal coming from the transmitter. You want to have a maximum loss of about 37 dB within about half a dB of accuracy. And here you can see where we've selected a particular transfer function based on the fixtures that we had used for this PCI Express 5.0 correlation test event that occurred a few weeks ago. Here you can see the test report that is generated by the D9050 PCIe, and in this case, it shows a passing result and some of the individual results associated with the 32 gigabit per second tests of the transmit de-emphasis coefficients for presets P0 through P10. Keysight has the broadest number of tools available for PCI Express 5.0 development available in the industry for physical layer test and validation. We start at the physical layer on the simulation side with our PathWave ADS design software. Physical layer interconnects and analysis of the channel is really crucial for Gen 5, and with our TDR tools and especially our VNA and PNA products, we're able to analyze channels and channel loss with an accuracy that's unmatched in the industry. Finally, our two tools for doing physical layer transmit and receiver test represent the best tools available in the industry, with the UXR series oscilloscope, which has the lowest noise floor in the industry, and the M8040 platform for physical layer test, which supports PCI Express Gen 5 and is also capable of supporting PAM4 operation well beyond the 32 gigabaud speed of PCI Express Gen 6. So you not only have solutions that work well with today's technology for Gen 5, but these tools provide you with a solid platform which to prepare for working on PCI Express 6.0 in the future. Speaking of PCI Express 6.0, I wanted to spend a little bit of time to give you a preview as to what you can expect to see for PCI Express version 6. This version, and I'll get into more detail, is designed to operate at 64 gigatransfers per second, which doubles the performance of PCI Express 5.0. One of the things that you'll notice about PCI Express 6.0 is that we will be introducing some new features, new capabilities, new signaling, and new types of signal encoding. Let's start off and discuss some of the new capabilities that you'll find in the PCI Express 6.0 specification. The first thing you'll notice is that PCI Express version 6 doubles the data rate of PCI Express version 5. And we do this by moving to PAM4 technology, which allows us to transmit 2 bits per symbol. PCI Express version 5, for example, only transmits 1 bit per symbol. So as such, we can say that both Gen 5 and Gen 6 are 32 gigabaud capable technologies, but PCI Express 5.0 operates with NRZ signaling, whereas PCI Express Gen 6 uses PAM4. Another thing that you'll find that's new with Gen 6 is the use of a low latency forward error correction. This allows PCI Express version 6 to operate at a lower native BER compared to PCI Express 5.0. Gen 5, for example, has a native BER of 1 error in 10 to the 12 bits. PCI Express Gen 6 has a native BER of 1 error in 10 to the 6 bits. Now, the link for both is the same, of 1 error in 10 to the 12 bits. But in the case of PCI Express 6.0, it's able to achieve that by using forward error correction. And one thing to keep in mind is that both Gen 5 and Gen 6 utilize the same channel bandwidth. So the Nyquist frequency of Gen 5 and the Nyquist frequency of Gen 6 are the same. So this allows us to leverage all of the learning and the substantial work that has gone into the PCI Express 5.0 channel definition. Now, of course, there are some changes in the connector and some things that have to improve, like crosstalk, for example, in the connector and in the channel. But this will go into some greater details than we have time to deal with here. So some of the key applications for PCI Express 6.0 include 800 gig Ethernet, where it's looking for more and more performance, artificial intelligence, or AI, the use of coprocessors and accelerators, which is common now in the data center, are all key applications that PCI Express 6.0 is targeted to support. PCI Express Gen 6 will also support IDE for data encryption and greater security. Now, channel reach for PCI Express Gen 6 will be slightly less than what we had for Gen 5. PAM4, for example, reduces the signal to noise ratio by a factor of about 9 dB, which is pretty significant. And this causes us to really have to think about what the native BER is and forces us to move to forward error correction technology so that we can fix that. We can get it back to 1 error in 10 to the 12 bits after FEC has been applied. Now, a big benefit of doing all of this is that PCI Express 6.0 will maintain backward compatibility with all previous revisions of PCI Express technology. But we also define a new type of packet. So from a protocol standpoint, Gen 6 is very different from PCI Express 5.0 with the introduction of the flow control unit, or FLIT. So this is a fixed set of bytes and represents a new packet type for PCI Express 6.0. Other goals that we had for PCI Express technology version 6 is that we wanted it to support high volume manufacturing. So we didn't want it to be too costly to implement. We wanted it to be testable. We wanted it to be simple. So we're working on completing now the 7.1 version of the base spec, and version 0.9 should be released in several months after the release of version 0.71. Here is a quick look at a PCI Express 6.0 TX compliance signal. So this signal is used for signal quality measurements for a PCI Express 6.0 signal. It is transmitting at 32 gigabaud. It is 64 gigabits per second. And you can see that with PAM4 signaling, we have 3 eyes, where previously with Gen 5, we would only have 1. And you can see here immediately that the signal to noise ratio associated with each eye is substantially reduced for PCI Express 6.0 compared to PCI Express 5.0. And this requires that the link be much more cognizant or aware of crosstalk that might exist in the channel, crosstalk that might be contributed by the connectors. Reflections, both near end and far end, can also impact the signal integrity of the link. Now, PCI Express 6.0 is also designed to operate with a channel that has about 31 dB of loss at 16 gigahertz. PCI Express Gen 5 could operate at a loss of about 37 dB in a channel at 16 gigahertz. So a slightly longer channel is possible with PCI Express Gen 5 compared to Gen 6. So that's one of the trade-offs of moving to the higher bandwidth and higher performance. PCI Express 6.0 will add new measurement challenges due to the PAM4 signaling that is employed by Gen 6 technology. So PCI Express Gen 6 isn't the first major technology to utilize PAM4 signaling. And in fact, IEEE 802.3 and OIF CEI 4.0 both came along some years ago utilizing PAM4 technology at lower data rates and now operate at higher data rates with PAM4. So the PCI SIG is looking to learn from those standards and is planning to incorporate additional measurements for handling PAM4 signaling, and 2 of those are shown here. One is the signal to noise and distortion ratio, or SNDR, and the other one is a multi-edge jitter measurement. Now we refer to that as JNU, but this could be, depending on the standard, something like J4U or J6U. So N is a number that has to do with the number of edges that the jitter algorithms are designed to measure. Now, what I talked about previously is that the native BER of 1 error in 10 to the 6 requires a low latency FEC in order to achieve high reliability of the link. So forward error correction is able to improve the overall link BER and will allow a Gen 6 system to achieve a system bit error ratio of 1 error in 10 to the 12 bits. Now, this also helps to make it easier to make the JNU measurements for jitter, because jitter again is measured at a estimated BER of 1 error in 10 to the 6 bits. Now, channel loss is going to be a significant factor for Gen 6. So we're targeting a PCB loss of about 1 dB per inch, and that's 1 dB in about 2.5 centimeters at 16 gigahertz. It's thought that we need this for server design because typically a server can have a long channel. It could be up to 50 centimeters with 2 connectors. Now, we acknowledge that some servers may have to use retimers in order to achieve that, but we're targeting an overall estimate of about 30 to 32 dB of channel length for a PCI Express Gen 6 channel without the use of a retimer. Now, an overall rule of thumb when you're using PAM4 signaling is that you can get up to a 1 dB reduction, or if you experience a 1 dB deduction, that this can increase the channel reach by about 1 inch or 2.5 centimeters at 16 gigahertz. So if you're able to utilize a lower loss material or a lower loss channel, then you can increase the overall reach of the PCI Express Gen 6 channel length that you use. For example, one of the things that we have seen in some systems is the use of cabling, which has much lower loss compared to many types of PCB traces. So with the use of cabling, for example, you may be able to extend the length beyond, say, 20 centimeters, which might be the limit of the channel if you were to implement it in PCB material. Now, we do also acknowledge that with Gen 6, we're going to need more aggressive transmit equalization, receiver equalization, and receiver DFE. So you'll see significant improvements and advances in all of those areas in the Gen 6 specification. PCI Express 6.0 signaling uses PAM4 or pulse amplitude modulation signaling. So I wanted to talk about that in a little bit more detail in case it may be unfamiliar to some. So you have 4 distinct levels that define 2 bits, as opposed to 2 levels that would define 1 bit for NRZ signaling. And again, the advantage is that we can transmit 2 bits per symbol within the same channel bandwidth that was established for PCI Express 5.0. Now, nothing comes for free. So we do this at the expense of reduced voltage levels, which is I height, and I width increases our susceptibility to errors. So we do a couple of things to help minimize those errors. So Gen 6 utilizes gray coding to help us minimize errors within the unit interval. We also use pre-coding. Pre-coding is required for PCI Express Gen 6 transmitters that helps us to eliminate or reduce the likelihood or the probability of incurring a burst error in the DFE. Burst errors can occur when you have a sequence of zeros and ones. So you have a 0, 1, 0, 1 in sequence, and pre-coding really eliminates that pathological pattern in the data. So the voltage levels at the transmitter and the receiver define the encoding. And so you can see here that the level that you're at defines either a 0, a 1, 1, a 0, 1, or a 1, 0. So you have essentially 4 bits that you can transmit within a single unit interval. This slide shows you some of the significant challenges of moving from NRZ to PAM4. With NRZ signaling, we are transmitting 1 bit per unit interval. With PAM4 technology, we are transmitting 2 bits per unit interval. But you can see the difference in the I height. And just by moving to PCI Express 6.0 and PAM4, we see a 1/3 reduction in the amplitude of the I. And this corresponds to a 9 dB reduction in the signal to noise ratio. And it also affects us by reducing the unit interval timing loss due to the level transitions, so it effectively makes the eyes more narrow. When you do this, you have some additional problems in signal integrity. You have greater sensitivity to noise. Noise is reflected in crosstalk, reflections that may exist in the channel, and other noise sources that can contribute to eye closure. And one of the things this is driving with PCI Express 6.0 technology is that we have to achieve a reduction of 1.5x in the total amount of allowable transmit jitter. Here you can see some of the channel estimates for PCI Express 6.0 compared with earlier generations. PCI Express Gen 5 minus 36 dB, Gen 6 minus 32 dB. So that will present some challenges in that it's a slightly shorter channel. Overall, we want to see about 20 centimeters of length with one connector, or with a retimer in place up to 50 centimeters in length to be able to support server architectures. Here's an estimate of routing lengths between Gen 5 and Gen 6. So you can see that overall system routing lengths are expected to be reduced moving to PCI Express 6.0, and that the overall budget allowances for adding cards is also reduced by about a dB. So this reflects greater challenges to be able to build systems without retimers, or will demand the use of lower loss materials or new architectural shifts in the use of cabling. With every successive generation of PCI Express technology, we see a significant reduction in two areas. One is the reduction in allowable transmit jitter, and the second area where we see a lot of attention being paid is to the amount of phase jitter that's allowable on the PCI Express reference clock. So phase jitter represents filtered jitter, which is jitter that falls within the TX PLL loop bandwidth. So we can see that for reference clocks in the system for common clock architectures, PCI Express 6.0 allows only 0.1 picoseconds or 100 femtoseconds of jitter on the reference clock. Now, based on measurements we have made with our oscilloscopes, we believe this is very easily measurable with the latest technology of scopes and software that takes advantage of noise reduction capabilities in the scope. But even without using noise reduction techniques, we've been able to measure jitter down around 0.04 picoseconds, so about 40 femtoseconds. So that's well below the passing limit that's being set for PCI Express 6.0. With PCI Express 6.0, our tools will be adding additional measurements to support PCI Express 6.0 measurement requirements. As was mentioned, we'll be dealing with signal to noise and distortion ratio, or SNDR, multi-edge jitter measurements, new reference clock jitter measurements. These are filtered phase jitter measurements, and we'll be having to work with technologies that include 3-tap TX equalization, 16-tap DFE, new equalization, new forward error correction, adjusting to a native BER of 1 error and 10 to the minus 6. And our overall techniques for doing receiver calibration will be substantially similar to test methods put in place for PCI Express 5.0. Let's go into some of the specifics of a few of these measurements. Let's start with the signal to noise and distortion ratio. This is pulled directly from one of the IEEE 802.3 specifications, where we're going to measure SNDR as the equation listed on the bottom of this screen. There are a number of terms: Pmax, sigma E, and sigma N. As we will be making this measurement on a real-time oscilloscope, one of the important measurements is sigma N, and we'll be getting into that in a little bit more detail. While the IEEE uses a sampling scope approach for measuring SNDR, the PCI SIG will be using a real-time oscilloscope to make this measurement. As such, some of the techniques that the IEEE used with the sampling scope don't readily apply directly to how we should make this measurement on a real-time oscilloscope. So Keysight worked with the PCI SIG and one other major vendor to put forth a new measurement technique for measuring sigma E as part of the SNDR calculation. SNDR is a combination of measuring three terms. One is Pmax, which is the linear fit pulse response. The other one is sigma E, which is the linear fit error waveform. Neither of these are substantially influenced by the noise floor of the real-time oscilloscope. However, the third portion, which is sigma N, is designed to measure the RMS deviation from a mean voltage. And this can be substantially influenced by the noise floor of the oscilloscope. So this requires that we take a new approach to measuring sigma N when measuring a PCI Express signal on a real-time oscilloscope. For PCI Express 6.0, we'll be measuring noise as part of symbol 61 on the flat spot for each of the main levels in the PCI Express Gen 6 TX compliance signal. And so here you can see an example of a signal in yellow and us making 8 evenly spaced measurements on that signal for noise within a single unit interval. So this is one symbol number 61, on a flat spot, and we are making a measurements which we will average across 250 repetitions. So this is how we get to a very consistent measurement of sigma N in the real-time oscilloscope. As part of the lab data that Keysight submitted to the PCI SIG, we investigated to determine whether there was a significant difference by picking different points in different symbols, or looking within those symbols to see if there was any difference in the measurement for sigma N. And what we showed was that the noise measurement we would make varied from acquisition to acquisition as a random process, which allowed us to greatly simplify and consolidate how the sigma N measurements should be made, and choosing to make 8 evenly spaced measurements on one of the flat regions of the TX compliance signal in symbol number 61. Another area where PCI Express 6.0 differs from PCI Express 5.0 is in the area of jitter. And here you can see jitter measurements for total uncorrelated jitter and uncorrelated total jitter when running with SSC, as well as uncorrelated DJ delta delta. So each of these three measurements for uncorrelated jitter have to be made according to different edges. For PAM4 signals, the edges have different slew rates depending on what the starting level is and what the final level is. And we'll get into that in a little more detail. One of the new measurements that was implemented as a direct result of supporting PAM4 technologies was the JNU jitter measurement. And here you can see an example here where the tool is able to measure 12 distinct edges of a PAM4 signal independently. Gen 6 consolidates all of these edge measurements into one jitter measurements for each of the main uncorrelated jitter parameters. Another important area for signal quality measurements for Gen 6 is going to be linearity. And here we want to make a measurement of how linear the spacing is for the different levels. We want those levels to be very consistent for each of the definitions for symbols 00, 01, 10, and 11. So for Gen 6, there are now going to be mandatory requirements of gray coding and pre-coding in the Gen 6 transmitter, and we'll have a target for signal to noise and distortion ratio of greater than 34 dB and a ratio of level mismatch for level measurements of greater than 0.95. Finally, when it comes to tools and solutions for supporting PCI Express early pathfinding, you'll notice that this tool selection here is exactly the same as it was for PCI Express 5.0. And this helps you to have the confidence that the Keysight tools you use for Gen 5 will give you the runway and platform from which to advance to PCI Express 6.0 technology.